Was there anything before the Big Bang? Okay, I need you to stay with me here because what I'm about to walk you through tonight is a question that has haunted the greatest minds in human history. And for decades, physicists told us the question itself was meaningless. They told us we weren't allowed to ask it, but something has changed, and I need you to understand what that change means. Was there anything before the Big Bang? For most of the last century, the answer was simple. The question doesn't make sense. The Big Bang created space. It created time. Asking what came before the Big Bang was like asking what's north of the North Pole. There's no before because time itself didn't exist yet. But here's the thing. The smartest physicists on the planet no longer believe that. In fact, a recent survey of leading physicists found that the majority of them have moved away from the idea that the Big Bang was the absolute beginning of everything. They now believe something came before it. And what that something might be is one of the most extraordinary stories in modern science. Let me take you through it. Here's what you need to understand. First, when we talk about the Big Bang, we're actually talking about two very different things. And almost nobody makes this distinction. There's what scientists call the hot Big Bang, which is the incredibly dense, incredibly hot early phase of the universe that we have overwhelming evidence for. We can see the afterglow of it. It's called the cosmic microwave background. It's real, it's measurable, it's one of the most studied things in all of physics. But then there's the Big Bang singularity. That's the mathematical point where the equations of Einstein's general relativity break down completely. Infinite density, infinite temperature, zero volume. Everything we know about physics collapses into nonsense. And for decades, that singularity was treated as the beginning of time itself. Here's the critical shift. Physicists are now separating those two ideas. The hot Big Bang absolutely happened, but the singularity, that might just be a sign that our math isn't good enough, not that the universe had a hard beginning. Think about what that means. If you're finding this valuable, make sure you subscribe to this channel right now and turn on notifications because I'm going to walk you through three competing theories about what existed before our universe. And one of them was just given extraordinary new support from a supercomputer simulation published in 2025. You don't want to miss what comes next. Let me start with the most mind-bending possibility. It's called Conformal Cyclic Cosmology, and it was proposed by Nobel Prize winning physicist Sir Roger Penrose. Penrose is one of the most brilliant mathematical physicists alive. He won the Nobel Prize in Physics in 2020 for his work on black holes. And his theory goes like this. Our universe is not the first and it won't be the last. What we call the Big Bang was not a beginning. It was a transition, a doorway between one cosmic era and the next. Stay with me here because this gets extraordinary. Penrose calls each era of the universe an aeon. Each aeon starts with a Big Bang, expands for trillions upon trillions of years, and eventually all the matter in the universe gets consumed by supermassive black holes. Those black holes then slowly evaporate through a process called Hawking radiation, named after Stephen Hawking. And after an incomprehensibly long time, the universe is left with nothing but light, pure radiation, no matter, no mass, nothing with any sense of size or time. And here's the key insight. When there's nothing left in the universe that has mass, the universe loses track of how big it is. Scale becomes meaningless. And mathematically, an infinitely large empty universe becomes indistinguishable from an infinitely small dense point. The end of one aeon becomes identical to the beginning of the next. Let me say that again so it lands properly. The death of one universe becomes the birth of the next, not metaphorically, mathematically, through what Penrose calls a conformal rescaling of spacetime. Now here's where it gets even more remarkable. In March 2025, Penrose and his colleague Krzysztof Meissner at the University of Warsaw published a major new paper. They use something called twistor theory to prove that there's a mathematical quantity that remains constant across the boundary between one aeon and the next, and invariant. And they showed that the masses of the largest black holes from the previous aeon lineup quantitatively with the temperatures of mysterious hotspots found in the cosmic microwave background. Think about what that means. If Penrose is right, we're not just theorizing about a previous universe. We may actually be seeing its fingerprints burned into the oldest light in our sky. Those hot spots, which Penrose calls Hawking points, could be the final signatures of supermassive black holes that evaporated in a universe that existed before ours. Now, I need to be straight with you, this is still very much debated. A study in 2020 argued that those hotspots could be explained by conventional physics once you account for something called the look elsewhere effect. Penrose pushed back hard on that analysis. The scientific community is divided, but the fact that we're even having this argument based on actual data from our actual sky is extraordinary. And here's what most people are missing. Penrose's theory doesn't require any exotic new physics. It doesn't require extra dimensions. It doesn't require string theory. It works within Einstein's general relativity. That's part of what makes it so elegant and so unsettling at the same time. But that's not even the most important part. There's a second theory, and it comes from a completely different branch of physics. It's called the Big Bounce, and it's built on a theory called loop quantum gravity. Here's the basic idea. Einstein's general relativity is extraordinary. It describes how gravity works, how space-time curves, how planets orbit and light bends. But at the very beginning of the universe, when everything was compressed into an unimaginably small space, Einstein's equations produced that singularity I mentioned. The math breaks down. Loop quantum gravity says the reason it breaks down is that Einstein didn't know about quantum mechanics at the scale of gravity. When you apply quantum physics to the fabric of space-time itself, you discover something stunning. Space is not smooth. Space is not continuous. At the smallest possible scale, space is made of tiny discrete loops, quantum threads woven together like a fabric. There is a minimum possible volume, a floor below which you cannot compress anything further. And this changes everything about the Big Bang. Stay with me here because this distinction matters enormously. In Einstein's equations, as you rewind the universe back toward the Big Bang, the density goes to infinity. There's no stopping point. The math just collapses. But in loop quantum gravity, there is a stopping point. The density reaches a maximum, what physicists call the Planck density, and then something extraordinary happens. Gravity, which has been pulling everything together, flips. It becomes repulsive, violently repulsive, and the universe bounces. That's the big bounce. Our universe didn't emerge from nothing. It emerged from the collapse of a previous universe. When that previous universe contracted to the point where quantum gravity effects kicked in, it rebounded outward in what we observe as the Big Bang. Abhay Ashtekar, Tomas Pawlowski, and Paramit Singh at Penn State University first demonstrated this mathematically in 2006, and since then the theory has been extended and refined by research groups around the world. Now here's why this matters right now. In August 2025, a team of physicists from King's College London, Queen Mary University of London, and Oxford University published a groundbreaking paper in Living Reviews in Relativity. They proposed using something called numerical relativity, which means using supercomputers to solve Einstein's equations in extreme conditions to actually simulate what happened before the Big Bang. Let me read you what one of the lead researchers, Eugene Lim of King's College London, said. He described how traditional methods are like searching around a lamppost. You can only solve the equations in simplified scenarios, but numerical relativity lets you explore the dark regions away from the lamppost. It lets you model conditions that no pen and paper math can handle. And they're not just modeling the Big Bounce. They're testing whether our universe might have collided with a neighboring universe. They're looking for bruises on the sky, signatures that would show up in the cosmic microwave background if another cosmos bumped into ours. They're modeling cyclic universes that endlessly bounce through creation and destruction. This is not science fiction. This is computational physics published in one of the most prestigious journals in the field. If you're learning something from this, hit that like button right now because this story is about to get significantly more complicated. And I want to make sure this reaches the people who need to see it, because here's where I need to connect some dots. While physicists are arguing about what came before the Big Bang, something else is happening right now that could change the entire conversation, and it involves the future of our universe. In March 2025, the dark energy spectroscopic instrument known as DESI released its most comprehensive data yet. DESI has built the largest three-dimensional map of the universe ever created, mapping nearly 15 million galaxies and quasars stretching back 11 billion years. Here's what you need to understand about why this matters for our question. Dark energy is the mysterious force that's pushing our universe apart. It makes up roughly 70% of everything in the cosmos. And for decades, scientists assumed dark energy was constant. It was baked into the equations as a fixed number, Einstein's cosmological constant. But the DESI data is showing something different. When the team combined their measurements with data from the cosmic microwave background, from exploding stars, from the way gravity bends light, they found mounting evidence that dark energy may be weakening over time. It's not constant, it's evolving, and here's why that's terrifying or beautiful, depending on how you look at it. If dark energy is weakening, then the expansion of the universe could eventually slow down. And if it slows enough, the expansion could stop entirely. And then the universe could start contracting, pulling back together, getting denser, getting hotter, until eventually it collapses into what would be the next big crunch. And then if loop quantum gravity is right, it would bounce a new Big Bang, a new universe. Professor Henry Tai at Cornell University and his team have been running detailed simulations of this exact scenario. Their model suggests that the universe's expansion may slow down and that a big crunch could happen in roughly 19 billion years from now. That's a long time by any human measure. But in cosmic terms, it means our universe might be roughly halfway through its life. Think about what that means. Now, I want to be very clear about something. We are not at the level of scientific certainty on any of this. The DESI results, while extraordinary, have not yet reached what physicists call 5 sigma, the gold standard for a discovery. Different combinations of the data range from 2.8 to 4.2 sigma. A 3 sigma result has about a 3 in 1,000 chance of being a statistical fluke. That's suggestive. It's exciting, but it's not proof. And the theories about what came before the Big Bang, whether it's Penrose's conformal cyclic cosmology or the big bounce from loop quantum gravity, remain vigorously debated. There are legitimate scientific criticisms of both. But here's what I don't think enough people appreciate. The fact that these are now testable questions is itself revolutionary. For decades, why what came before the Big Bang was a philosophical question. It was the kind of thing you might discuss over dinner, but that serious physicists would dismiss as unanswerable. That era is over. We now have mathematical frameworks that make specific testable predictions. We have supercomputers powerful enough to simulate pre-Big Bang conditions. We have instruments like DESI mapping the structure of the cosmos with unprecedented precision. And we have the cosmic microwave background, the oldest light in the universe, which might be carrying signals from before our universe even existed. Drop a comment right now. Tell me where you're watching from. I want to know how far this is reaching, because these are the kinds of stories that don't get enough attention. And the only way that changes is if you engage. Now, let me bring this home. There's a third possibility I want to leave you with, and in some ways, it's the most unsettling of all. It's the idea that asking what came before the Big Bang might not be wrong, but it might be the wrong kind of question. Some physicists working on quantum gravity suggest that time near the Big Bang doesn't work the way we think it does. Time doesn't just slow down. It becomes fuzzy, uncertain. It might transition from what we experience as normal time into something more like a spatial dimension. Stephen Hawking and James Hartle proposed a version of this decades ago. They called it the no-boundary proposal. In their model, asking what came before the Big Bang is indeed like asking what's south of the South Pole. Not because time began, but because the nature of time changed into something for which before has no meaning. Here's the thing. Each of these theories, Penrose's cyclic aeons, the quantum big bounce, the no-boundary proposal, they all agree on one thing. The old picture of the Big Bang as an absolute beginning, a moment where everything came from nothing, is almost certainly wrong. Something more complex, more subtle, and more beautiful is going on. Let me leave you with 3 things. First, the question of what existed before the Big Bang has moved from philosophy into physics. Real data from the cosmic microwave background from DESI, from gravitational wave detectors, is now being used to test specific predictions about pre-Big Bang conditions. This is no longer speculation, it is science at the frontier. Second, the leading theories, whether cyclic cosmology, the Big Bounce, or something else entirely, all suggest that our universe is not a one-time event. It may be part of something larger, something that stretches back before our Big Bang and will continue long after our universe goes dark. The implications of that for our understanding of existence are almost too large to comprehend. Third, the DESI results about weakening dark energy could be the most important cosmological finding of our generation. If confirmed, it doesn't just change our understanding of how the universe will end, it changes our understanding of how it began, because a universe that can contract can bounce. And a universe that bounces might have been bouncing forever. Here's what to watch for. The DESI collaboration will continue collecting data. The Euclid Space Telescope, launched by the European Space Agency, is already mapping the cosmos. NASA's Nancy Grace Roman Space Telescope is set to launch in 2027. Each of these instruments will provide new data that could push us past that 5 sigma threshold. If dark energy is truly evolving, we could know for certain within the next few years. And the teams working on numerical relativity simulations of the pre-Big Bang universe are just getting started. As computing power increases, their models will become more sophisticated, their predictions more specific, and their ability to match those predictions against real observations will improve dramatically. We are right now in one of those moments in the history of science where the questions we're asking are getting bigger than the answers we have. And that is always where the most important discoveries come from. 13.8 billion years ago, something happened. It might have been a beginning. It might have been a transition. It might have been one beat in an infinite cosmic heartbeat that has been pulsing since before time had any meaning. We don't know yet. But for the first time in human history, we have the tools to find out. And that is not nothing. Make sure you're subscribed with notifications turned on, because this story is far from finished. The data coming in over the next 2 to 3 years could fundamentally rewrite everything we think we know about where we came from. I'll be here to walk you through every development. I'll be watching, and so should you.